Welcome to Your Math Explained, where we make math simple and clear. My name's Angela. If I ask you to solve the equation x squared minus 4 is equal to 0, you can do it in your head. And if I asked you to solve x squared minus 5 is equal to 0, you can use the quadratic formula. But what happens if you need to find the roots of something like x to the power of 5 minus x minus 1 is equal to 0, or some other quintic polynomial, or something like x is equal to cosine of x? There are no clean algebraic formulas for these. Back in the late 1600s, Sir Isaac Newton faced this exact problem while calculating planetary orbits. He realized that if you can't solve an equation directly, you can use calculus to generate closer and closer approximations. And this linear iteration process is now known as Newton's method. Now, before we dive in, if you haven't subscribed to the channel yet, make sure you do that first so you don't miss out on new weekly content. The logic of this method is quite beautiful. You pick a starting x value, let's call it x naught, that's somewhere near the root. And then we're going to draw a tangent line at that point, and where the tangent line crosses the x-axis, that's going to become the next guess. So this Newton's method formula here says that if we have our nth guess, which is x sub n, we can calculate the next guess, which is x sub n plus 1, as x sub n minus f of xn divided by f prime of x sub n. So let's take a look at why that is the case. So we're going to go ahead and draw our axes, and then let's say we have some random curve that crosses the x-axis, but we don't know where this root is. So if we start with our first guess, let's say somewhere around here, that is going to be our x naught. Then this point is going to be x naught comma f of x naught. So then what we do next is we're going to draw a tangent line to that point. So this would be our tangent line to the point here. And then where this tangent line crosses the x-axis, which would be right over here, this is going to be our next guess. Now how this formula is derived is this. The equation of this tangent line here is going to be y minus the y value of our dot, which is f of x naught. And this is equal to the slope, which is f prime of x naught, multiplied by x minus x naught. And since we want to find where this line intersects the x-axis, we know that that point is at x1 comma 0. So meaning our y value here is 0. So we have 0 minus f of x naught is equal to f prime of x naught multiplied by, and then the x value there is x1. So we have x1 minus x naught. So now isolating x1, we get x1 is equal to x naught minus f of x naught over f prime of x naught. And this is exactly this equation here. It's just that n here is equal to 0. And we basically keep iterating this. So at x1, we would have this point here. And then what we're going to do is we're going to draw a tangent to that point. And then where it intersects the x-axis, that is going to be our next point. So that would be our x2. And you keep repeating this using this formula here. And the algorithm logs onto the actual root with blistering speed. And as you can see in this example here, we started with our initial guess of x naught, and we repeated this process twice, and x2 is already very close to the actual root. Now you will need a calculator to do this, so make sure you have a device with you and follow along. For our first example, we want to approximate the real root of this function here by using a starting guess of x naught equals 2. So using the formula, we would have x1 is equal to x naught minus f of x naught over f prime of x naught. Which means before we can actually evaluate everything, we need to first find what the derivative is. So here our f prime of x is going to be equal to 3x squared minus 2. So therefore x1 is going to be equal to 2 minus 2 cubed minus 2 times 2 minus 5 over 3 times 2 squared minus 2. And this is equal to 2 minus -1 over 10. So this means our x1 is going to be equal to 2.1. So now our x1 is already pretty close to x0. But let's go ahead and do one more step. So that means x2 is going to be equal to x1 minus f of x1 over f prime of x1. So x2 is going to be 2.1 minus 2.1 cubed minus 2 times 2.1 minus 5 over 3 times 2.1 squared minus 2. And this is roughly 2.0946. And just to take a look at what the function actually looks like, here I've plotted the function f of x, and we can see that the root here is 2.09455. So this means in just 2 steps, we went from a rough guess to a value that's accurate to 4 decimal places. And if we were to continue this process, the approximation is going to become more and more accurate. But for this example, we can stop here. For our next example, we want to find where x is equal to cos x using a starting guess of x0 is equal to 1. So here, the first thing we need to do is to rewrite the equation, because to use Newton's method, we're approximating a root, which means we need a function f of x is equal to 0. So that means we're going to move everything to one side of this equation. So we're going to let f of x be equal to x minus cosine of x. And if you have moved everything to the other side, the function cos x minus x is also okay. So now we get f prime of x is equal to 1 plus sine x. This means our x1 is going to be our x0, which is 1, minus f of x0, so that'll be 1 minus cosine of 1 over f prime of x0, which would be 1 plus sine of 1. And this roughly evaluates to 0.7504. If this is not the answer that you got, make sure you double check your calculator settings to see if it's in radians mode. And now we're going to repeat this process and find x2. So x2 is going to be 0.7504 minus 0.7504 minus cosine of 0.7504 over 1 plus sine of 0.7504. And this roughly evaluates to 0.7391. And again, just to double check, our actual root here is 0.73909. So again, in just 2 steps, we are now accurate to 4 decimal places. Now for our last example, we want to use Newton's method to approximate the 5th root of 33 to 3 decimal places. And we're going to start with an initial guess of 2. So again, here we need to set up our equation first. So if we let our answer x be equal to the 5th root of 33, then that means x to the power of 5 is equal to 33, which means if we want to have a function f of x and approximate the root of the function, we would set our function f of x to be equal to x to the power of 5 minus 33. So this means our derivative f prime of x is going to be 5 times x to the power of 4. So now the question wants us to approximate this to 3 decimal places, which means we would keep iterating until our guesses are the same up to 3 decimal places. So our first one is x1, and this is going to be equal to 2 minus 2 to the power of 5 minus 33 over 5 times 2 to the power of 4. And this is equal to 2.0125. Now our x2 is going to be equal to 2.0125 minus 2.0125 to the power of 5 minus 33 over 5 times 2.0125 to the power of 4. And this is roughly equal to 2.0123. So if we look our x1 and we round it to the third decimal place, this is 2.013. And then our x2 rounded to the third decimal place would be 2.012. So right now they're still different, which means we need to go ahead and do one more. So we would have x3 is equal to our x2, and make sure that when you're doing this, you're inputting the full value of x2 and not the rounded number for x2. So we would use x2, and then that would be minus f of x2 over f prime of x2. So if we use the full value of x2, this is roughly 2.012346. But we don't care about all those decimal places, because if we round this to the third decimal place, this is 2.012. And now our x2 and x3 are the same. So this is where we can stop. So therefore, our answer for the fifth root of 33, accurate to 3 decimal places, is going to be 2.012. And now let's do a quick recap of what we covered in this video. Newton's method is a good example of linear approximation in action. It works by continually swapping out a complex curve for a simple tangent line to hunt down its root. And as we saw in the later example, the setup matters. We always need to rearrange our target equation into something of the form f of x is equal to 0 before we can start using Newton's method. And lastly, we didn't see this in any of our examples, but if our initial guess lands on a local maximum or a local minimum, then that means the derivative is going to be equal to 0, and the formula is going to break down completely because we can't divide it by 0. So therefore, a good first guess that is close to the root is essential for the success of this method. And there are actually a couple of other situations where Newton's method breaks down, but they are beyond the scope of this video. And now it is your turn to give this a try. Can you find the solution to the problem on the screen here? Make sure to leave your answer in the comments below and let us know what other calculus topics you'd like to see in the future. That's it for this video. If you found it helpful, remember to hit that like and subscribe. And if there's a topic you'd like us to cover, make sure to drop it in the comments.